Hello there, and welcome to another IB Math Speedrun with me, Vince. So we're going to be continuing our discussion with limits, and we're going to be discussing how they can relate to asymptotes that we see in graphs. So let's jump right in. So I hope you're familiar with what an asymptote is, but in case you're not, let's draw a simple y equals 1 over x graph. And an asymptote is a line that the graph tends to but never touches. So in this case, x equals 0 is an asymptote, a vertical one, and y equals 0 is a horizontal asymptote. If we graph this properly, 1 over x, as you can see, the line approaches 0 but never touches it. So we can use limits to define asymptotes a bit better. So the line x equals some constant is an asymptote if of a graph of the function y equals f of x if either the limit of as x tends to the positive of a constant, f of x is equal to plus or minus infinity, or the limit as x tends to c from the negative side is equal to plus or minus infinity. And we can see this on this graph. As you can see, setting our constant as 0 as x approaches 0 from the positive side, the value of y approaches infinity. It keeps on going up and up and up and down and down and down. And so this is a vertical asymptote. Now, how about horizontal asymptotes? Well, they're pretty similar. It's the line y equals k is a horizontal asymptote of y equals f of x if either the limit as x approaches infinity, positive infinity, of f of x is equal to k, or the limit as x approaches negative infinity of f of x is equal to k. So in this case, we can also see this as x approaches infinity, y gets closer and closer to 0, and that's why the line y equals 0 is an asymptote of this graph. Yeah. And there's one more thing we need to talk about, and it's called an oblique asymptote. And to show it, we would have to graph something like y equals, say, x plus 2 plus 1 over x. So in this case, we can actually see we have some sort of asymptote. Remove x, just go x plus 1 over x. We have some sort of asymptote here that's neither a horizontal line nor a vertical line. It's kind of a slanted line with the equation y equals x. So as you can see, this red line tends towards this blue line, but can never actually reach it. There's a gap between the two. And this kind of asymptote that's neither horizontal nor vertical is called an oblique asymptote or a slant asymptote. And so any rational function that is like equal to f of x over g of x, where the degree of f of x is 1 less than g of x, will have an oblique asymptote. Because when we divide f of x by g of x, we get another function, h of x, plus r of x over g of x, which is the remainder. So this is actually this would be the quotient, really. Q of x plus r of x over g of x. And the equation of the asymptote will be the quotient when we divide the two without the remainder. So yeah, so that's asymptotes, and now we need to talk a bit about the properties of some limits. So we can dive into solving some limits algebraically. So if we have two limits, limit as x approaches infinity of two functions, f of x plus or minus g of x, well, this will be equal to the limit of f of x, which we'll call L1, plus the limit of g of x, which is L2. So yeah, we can sort of add the limits in a sense to get the first limit. So this is actually equivalent to limit of x as x approaches infinity of f of x plus the limit as x approaches infinity of g of x. Same thing, which evaluates to that. Okay, next, if we're multiplying equations together, say the limit as x approaches infinity of two functions multiplied together, so f of x times g of x, well, we can also break this apart, and so we can say this is equal to the limit as x approaches infinity of f of x times the limit as x approaches infinity of g of x. So something like this would work. And so this is equal to L1 times L2, of course. It's the same for dividing the functions, as long as g of x is not equal to 0, that in limit as x approaches infinity of f of x over g of x is equal to the separate two limits, the limit as x approaches infinity of f of x divided by the limit as x approaches infinity of g of x. And so this is equal to L1 over L2, provided, of course, L2 is not equal to 0. Okay, next, we can bring constants out of limits because the limit of a constant is simply the constant itself. So if we have the limit as x approaches infinity of k f of x, this is equal to k times the limit as x approaches 0 of f of x. Same thing. And finally, we have the limit as x approaches infinity of, say, f of x to the power of a over b is equal to, we can take this power out of the equation, and so this will be equal to the limit of f of x to the a over b, provided that, of course, this is a real number, and a over b must be a rational number. Yeah. So this holds true for all limits, not just when they're tending to infinity, but when they're tending to any constant too. So with that being said, we can now jump into some problems, which there are a lot of. So I'll be doing the odd ones this time. So we have, first, we need to find the required limit. The limit of x as x tends to 3 of x plus 2 over x minus 2. And we can use the property we have earlier, that this is equal to the limit as x tends to 3 of x plus 2 over the limit as x tends to 3 of x minus 2, which is simply 4 over 2, which is equal to 2. So that is the first answer. Okay, on to the next question. Oh, sorry, no, I was like, did I make a silly mistake? This should not be that. This should actually be, what am I doing? We did limits and then I can't add numbers. 3 plus 2 is 5. 3 minus 2 is 1. So this should be 5 over 1, which is actually equal to 5. Okay, on to the next one. We have the limit as x tends to, I need to zoom in. As x tends to 3 times the square root of 3 of x to the 6 minus 9 over x cubed minus 3. And I would say this limit is not possible because, well, let's just check first, you know what. So this, actually no, this is possible. This is x to the, well, we can change that top part to x cubed plus 3 times x cubed minus 3. And we can say that this is equal to the limit of x cubed plus 3 as x tends to root 3 times the limit of x tends to 3 over root 3 of x cubed minus 3 over x cubed minus 3. So the thing is, this should tend to 1, even though it will never reach it since we cannot evaluate 0 over 0. But since it's a limit, we can evaluate it as 1. And so we simply have to evaluate this. And this will simply be 3 plus 3, otherwise 6. So yeah, that should be our limit for the third one. So next question, we have the limit of x squared minus 4 over x squared minus 2x as x approaches 0. Okay. So, well, we know we can evaluate this a little. We know this is equal to x plus 2 times x minus 2 over x times x minus 2. So we can actually get this, here's like a cheat thing. If we know that this thing exists, where we have one thing over the other in a limit, even if the limit tends to 0, we can evaluate this as 1 normally. And so we're left with the limit of x plus 2 over x as x tends to 0. Okay, now this can get a bit tricky because, yeah, we can't evaluate this because we're making x tend to 0, and this is normally just not possible. So we would label this limit as undefined or none. This does not exist. Okay, finally, we have the limit of 2 plus 3x squared minus 4 times 1 plus x squared over 6x as x tends to 0. So the first thing I would do is try and simplify this equation. So we have 4 plus 12x plus 9x squared minus 4 minus 8x minus 4x squared. And so this would be equal to, we would have 5x squared minus plus 4x over 6x, and we can factor this out into x times 5x plus 4 over 6 times x. And so even if we're getting the limit as x tends to 0, since we have x over x, we can therefore get limit of x tends to 0 of 5x plus 4 over 6. Because this will be equal to, limit as x tends to 0 of x over x, which will tend to 1, as x tends to 0 from both sides. So we can ignore that and simply get this. As x tends to 0, this tends to 2/3. Since 5 times 0 plus 4 over 6 is equal to 2/3, so this will be equal to 2/3. So that's the answer. Okay, now on to some more questions. And yeah, so we'll be moving on to the next set of questions, and those will be asking us questions where we need to find the limit as x tends to infinity. So the first question is we need to find the limit as x tends to infinity of 3x over x plus 3. And to solve these questions where they tend to infinity, the trick we need to use is we need to divide both the numerator and the denominator by x, or by the highest power of x. So this would be equal to the limit as x tends to infinity of 3 over 1 plus 3 over x. And so this would be equal to the limit as x tends to infinity of 3 over the limit as x tends to the infinity of 1 plus 3 over x. We know this top part is equal to simply 3, and this bottom part, as x tends to infinity, 3 over x will tend to 0, so this will be equal to 1, so this is equal to simply 3. That's it. So on to the next one. We need to find the limit as x tends to infinity of negative x squared plus x plus 2, oh, that's weird, what just happened, over 3x squared plus 2x minus 1. Okay. And so, well, we need to divide all of this by the highest power of x, so this will be equal to the limit as x tends to infinity, that's 8 on infinity, of negative 1 plus 1 over x plus 2 over x squared over the limit as x tends to infinity of 3 plus 2 over x minus 1 over x squared. And the trick is, any term that's being divided by x as x tends to infinity will tend to 1. So this will simply be equal to negative 1 plus, well, I guess 1 plus 1 over 3 plus 1 minus 1. X squared, yeah. And so this would simply be equal to 1/3. Yeah. Oh wait, no, sorry, no. I'm getting mixed up. So, sorry, any term that's being divided by x, as x tends to infinity, will tend to 0, since it just gets smaller and smaller and will eventually reach 0. So the final equation is simply negative 1/3. My bad. Yeah. Okay, on to the next one. So the next one we need to get 2x plus 3 over 5x squared minus 2. The limit as x tends to infinity of this. And so, well, what do we get? If we divide both top and bottom by x squared, we get the limit as x tends to infinity of 2 over x plus 3 over x squared over the limit as x tends to infinity of 5 minus 2 over x squared. So the thing is, this is equal to 0, this is equal to 0, so it's just 0 over 5, which is equal to 0. So yeah, that one was pretty simple. So on to the next one. And for the final one, we have f of x is equal to, find the limit as x tends to infinity of x plus 2 times x minus 1 over 2x. And I don't think there is a limit for this, because, okay, this series does not converge. This does not converge. So if we, what's it called? If we divide everything by x squared, what we get is the limit as x tends to infinity of 1 plus 1 over x plus, oh sorry, no, really just x plus 1 minus 2 over x. So what we want to do is divide by the largest power of x in the denominator, and so this will be equal to x plus 1 minus 2 over x over 2. As x tends to infinity, this thing, well, is really undefined. There's no limit, because it just keeps on going and going. Because we have x minus 2 over x. So as x tends to infinity, this gets larger and larger, this gets smaller and smaller, so there's no solution. Okay, finally we need to find some vertical and horizontal asymptotes. So the first function is we need to find vertical and horizontal asymptotes of 3x over 6x minus 1. And so remember, vertical asymptotes are when the limit as x tends to this a of f of x is equal to plus or minus infinity, and horizontal asymptotes are when the limit as x tends to infinity of f of x is equal to actually plus or minus. So for this function, well, for what values of a will f of x tend to plus or minus infinity, it will be when this denominator tends to 0. So in a sense, this would be, let's divide both the top and the bottom by x. So we get 3 over 6 minus 1 over x. And so, actually, sorry, this is solving for the horizontal asymptote. For the vertical asymptote, well, the limit must be equal to plus or minus infinity, and so we can simply look at the denominator. When does 6x minus 1 tend to 0, which makes the entire expression tend to infinity? It's when x is equal to 1/6. So this will be a vertical asymptote of this graph. Horizontal asymptotes mean that this needs to tend to a constant. The limit of, as x approaches infinity of this, will be equal to a constant, and that will be equal to 1/2. So y equals 1/2 should also be a horizontal asymptote of this graph. So x equals 1/6 and y equals 1/2 are both asymptotes of this graph. Okay, on to the next one. We have we need to find vertical and horizontal asymptotes of 1 minus x cubed over x squared minus 1, x cubed minus 1. So first, what values of x make this function tend to infinity? Well, it will be all values that make this denominator tend to 0, in this case, 1. So x equals 1 would be an asymptote of this graph. And secondly, well, what values does this get when it tends to infinity? Well, we can get that by getting the limit as x tends to infinity of negative x cubed minus x plus 1 over x cubed minus 1. And dividing everything by x cubed, we get negative 1 minus 1 over x squared plus 1 over x cubed over 1 minus 1 over x cubed. So this will be equal, the limit as x tends to infinity of this, which will be equal to negative 1 over 1, which is negative 1. So x equals 1 and y equals negative 1 will both be asymptotes of this graph. Finally, our final function is we have 3x cubed minus x over x squared. And so we need to find vertical and horizontal asymptotes. So the thing about this graph is, okay, first of all, x equals 0 is a vertical asymptote, clearly, because even though we can factor this into, say, x times 3x squared minus 1 over x times x, this will still have a vertical asymptote when x equals 0. Now we want to check for any horizontal asymptotes, but the thing is, I don't think this function converges. Let's try and take the limit. The limit as x tends to infinity of this will be equal to, let's divide 3x minus 1 over x over 1. And as you can see, this will keep on growing and growing as x tends to infinity. So there's no vertical asymptote, and there's no horizontal asymptote, and the only vertical asymptote is x equals 0. So yeah, that was it for the speedrun. I hope you enjoyed and learned more about asymptotes, and I hope to see you in the next one.